We are on Module 3, Lecture 3, and this module set of PowerPoints is going to be broken down into quite a number of smaller, more digestible pieces. So we've taken a look at the atmosphere. We've got a good idea of what is in the atmosphere. We understand a bit of the atmospheric profile, how temperature and function change through the atmosphere. And now we really need to understand how that energy, as it's transmitted through the atmosphere, is going to then produce weather and climate in certain locations at certain times. So this is really where the geography starts to take place in the atmosphere. Is all about location and timing of that solar energy coming in and how it then manifests into a locational phenomena. So to recap really quick, you know that the electromagnetic spectrum is the volume of energy at different wavelengths which are being emitted from by the sun and any other body. And as solar energy is being transmitted towards the surface of the earth, it's going to interact with the atmosphere. And as it interacts with the atmosphere, each photon is going to hit a particle or a gas molecule in the atmosphere. Once it does so, it's going to then transfer some of that energy, and by transferring some of that energy, the wavelength is going to get longer. Virtually then, with the transmission of from a shorter wavelength to a longer wavelength, we're going to then infuse the particle or the gas molecule that was interacted with the photon of light with some storage capacity, and then that's going to then also transmit into what you and I consider sensible heat that we can feel. When we talk about solar energy coming in, we're going to use the term insolation. And insolation basically is the amount of energy that is received by the Earth at a particular given location. So how much solar energy is being received at the equator on March 21st versus Pittsburgh on March 21st. That volume of insulation, think to insulate a thermos or insulate your house, is the storage capacity of energy at a particular time. So how much energy is in the atmosphere at that time? So that amount of insulation is then going to be variable based on season. And those seasonal factors are what's the tilt of the Earth? And the tilt of the Earth is going to determine which face of the Earth is facing the sun and which part of the Earth is not facing the sun. Recall that changes through season, but that also changes day and night, right? The Earth's distance from the sun is going to amount to some variability in the amount of solar energy. So think of standing in front of a campfire. And if you're pretty close to the fire, you're going to feel quite a bit of heat. If you back up a foot or two, the volume of heat that you're going to feel is going to diminish. And if you back up another couple of feet, then the volume of heat that you're going to feel is going to diminish accordingly further and further as you get away from the fire, campfire. Please remember that the elliptic orbit that we have around our sun, the difference between our winter relationship to the sun, which is relatively close, and our summer relationship to the sun, which is rather far, for the northern hemisphere, really isn't that much. The drawings show it quite significant, but the distance doesn't contribute to a whole lot difference in the volume of sunlight that our Earth receives from the sun. So it's not a big factor. Latitude is a much bigger factor that plays into how much energy is received at a particular location at a particular point in time rather than distance. So when you're facing away from the sun based on latitude, in the winter hemisphere, you're facing away from the sun, so you're going to get much less solar energy, much less insolation, as opposed to when you are in your summer hemisphere. When you are facing the sun, you're going to get a significant amount more solar insolation coming in. Additionally, local atmosphere and surface conditions, which we're going to talk about to some degree in the next set of slides for this module, really also play an important factor in how much insulation is received and retained at particular locations. So think atmospheric dust. The more dust you have is going to play into how much insolation is going to be received at the surface of the earth, which is going to be translated into heat. Think how much cloud cover you have. The more cloud cover you have, that cloud is going to act in two ways. If you recall from the last module, it's either going to deflect and reduce the amount of solar insolation at a particular location, and it's also going to retain solar insolation as heat units that's trying to escape the earth. All right, so those are two examples of what local atmospheric conditions can do. Local surface conditions play into the amount of solar insolation by way of a couple of different factors, and those include the surface's albedo, how much reflection there is, and the Earth's composition in terms of, is it land and opaque and it's going to not be able to transmit energy into deeper surface layers and then store that energy and then re-radiate later on? Or is it water, and what is the density of that water? So nice clear water, you're going to be able to transmit that energy nice deep into that body of water and then store that energy for a whole lot longer. That means that the surface is a little bit cooler, but at the time that solar energy is coming in, but it's going to re-radiate that energy at a later date. So it modulates the energy, as opposed to the surface area, which is terrestrial, has less modulating capacity. All right, so all in all, the combination of the Earth's orbit, how far close we are away from the sun, the tilt of our axis, which is going to determine our seasonality, and the atmospheric content, the stuff in our atmosphere, are the primary drivers for the temperatures that are going to be at a particular location. And then the secondary factor is, what is the surface of the Earth doing? All right, so we know that the volume of the solar insolation as it hits the Earth, for the most part, is equal as it's entering the surface of the Earth, but the the surface spherical nature of our Earth is going to result in the areas which are receiving direct sunlight at a perpendicular to the incoming solar radiation are going to have more dense sunlight per unit of area. So over the course of 12 months, solar energy is going to be pretty direct between 23.5 degrees north latitude, 0 degrees latitude, and 23.5 degrees south latitude. That's the margin of direct solar insolation over the course of a year. So as you're tracking that sunlight, as it moves into the northern hemisphere, anywhere where you have perpendicular solar energy, that's going to have the maximum amount of solar intensity for that location. And that solar angle is going to only travel at a 90 degrees or perpendicular to the surface of the Earth up until 23.5 degrees north latitude. On June 21st or 22nd, that's the maximum in the northern hemisphere latitudinally that we're going to get a perpendicular, direct, intense solar energy. Post the summer solstice, that sun's going to track back towards the equator, carrying direct solar energy at a perpendicular incidence with it until you get to September 21st or 22nd, which is the equinox. And then that solar energy is going to track into the southern hemisphere perpendicularly through to December 21st, which is our winter solstice, the summer hemisphere's summer solstice, perpendicular light to 23.5 degrees south latitude on December 21st or 22nd, depending on the year. Then it'll track back towards the equator for March 21st, 22nd. So this is the zone, if you will, where we're going to get direct sunlight at some point during the day. Because we've got nice direct sunlight, we've got lots of energy coming in. That means we've got lots and lots of solar insolation in these environments. It's going to drive the hydrological cycle. So we're going to have lots and lots of evaporation, which is going to produce lots of cloud cover. Lots of cloud cover is the storage effectively of solar energy within the water molecule, and that water molecule is then going to precipitate that energy out over terrestrial land masses and transfer that energy into ecosystems. So think of our large forest equatorial systems with the Congo, the jungles of places like the Philippines, and then of course the rainforests of Brazil. All right, wonderful, thick, high density, high energy capacity ecosystems. As we move above 23.5 degrees north latitude and above 23.5 degrees south latitude, the angle of incidence diminishes. And you can see that right here in the slide. So perpendicular, this is the amount of solar energy we're getting, but now we're spreading the same volume of energy coming in at this direct location over a greater surface area. So every location in mid-latitudes between 23.5 degrees north and south and about 60 degrees north and south, those are our mid-latitudes, we're going to get a diminished volume of energy. And the variability of that energy is going to be significant over the course of a year. That's going to translate into seasons. So our high energy seasons are our summers, our low energy seasons are our winters, and the transitional seasons between summer and winter and then summer and winter again are spring and fall. All right, so that's where we're going to get solar variability, is as that energy is tracking across those spring and fall months. That variability then, because we're getting less solar energy across these latitudes, we get the response of seasonality with plants and ecosystems at this time. So when we've got low solar energy coming in during winter months, ecosystems generally go into a more dormant phase. When we are transitioning that energy and we're bringing moisture from lower latitudes through air masses in clouds, we're going to get a pulse of growth and generation during spring months into our summer months. Our summer months are high energy intensive periods. Sometimes we see a deficit of solar energy transfer through water at those months. So we get a little bit of a drought season during the summer. And then our fall, our solar energy is being moved back through towards the southern hemisphere. And consequently, then we get a transition and a little bit more moisture again. And that moisture is going to give us a little bit of pulse of some plant activity. So we see this relationship in this regard at these mid-latitudes. But we also see, because there's less solar energy coming in per unit area, per square kilometer, per square mile, there's less energy. So the ecosystem's structure, what it looks like, is going to be different. So imagine the difference between what the rainforest looks like. And if you're not certain, take a look at a Google image of the rainforest, and then Google the forest in Pennsylvania or the forest in Ohio, and you'll see a structural difference. And the structural difference is because we've got less solar energy coming in at this latitude in and around Pennsylvania and Ohio. Move that solar energy farther north and farther south, and you see the angle of incidence is even greater. That means we've got even less solar energy per square mile or square kilometer occurring. If there's less energy available, then the ecosystem is going to respond similarly, and there's going to be less productivity. So this is where we're going to get our tundras, and with tundras we're also going to get boreal forests, and boreal forest structures look a whole lot different than our hardwood forests here in Pennsylvania and Ohio. Think conifer trees, think Christmas trees, and then above that, as you get into the more higher latitudes here, that's when you're going to get into lichens and mosses. So you're going to see a diminished volume of energy represented as a diminished volume of ecosystem structure. And recall that even though we're getting 24 hours of sunlight at a lot of these high latitudes, that sunlight is not coming in really intently, so we're not getting enough to produce a nice, big, robust ecosystem. All right. We translate that volume of solar energy into heat units, and we can recognize areas that are in our low latitudes, right here in this band that's rather pink, as energy surplus areas. These areas are getting an enormous amount of energy every day, all year round. Lots and lots and lots of energy. Boom, right here. That energy then moves to the north and moves to the south, seasonality. But if we average every day's energy through this zone, we've got a surplus for the most part of solar energy for these locations. The good thing is as the Earth rotates and moves, it redistributes this solar energy into higher latitudes. So these mid latitudes that we live in, so we're right in here. If you take a little look, we can see the Great Lakes, and imagine that we're just below Lake Erie here. We're right in the middle of the mid latitudes where we're getting transition. This is that sweet zone that we talked about a little while ago. Sort of the Goldilocks zone. Not too hot, not too cold. It's not too hot because we're not getting that direct sunlight every day, but it's not too cold where we're not getting enough solar energy. As we move northward, even though we're getting 24 hours again solar energy in the summertime, and likewise down here, summertime's 24 hours of solar energy for multiple days at a time to multiple weeks. There's insignificant or insufficient amount of energy coming in daily to adequately provide enough energy on its own at this location to supply the functionality of these aquatic ecosystems and these terrestrial ecosystems. So consequently, the energy has to rotate from these latitudes into the Arctic and into the Antarctic to help offset that deficit of energy. And that mixing is caused by the Coriolis. The spin of the Earth causes the Coriolis effect, which then rotates that energy. And just to recap, the other day we said that in the northern hemisphere, the Coriolis rotates clockwise, and in the southern hemisphere, it rotates counterclockwise. That means we're going to pick up nice warm energy from the equatorial areas, and they're going to distribute warm currents and warm air through the eastern shorelines of the northern hemisphere, of North America, and then we're going to rotate around past Greenland, past Iceland. Here is the British Isles. We're going to rotate around, and we're going to then pick up cold water and cooler air, and we're going to infuse these low latitudes with cool air where they're going to be warmed up. Southern hemisphere, this is the east coast, so we're going to rotate counterclockwise here. Nice warm energy all the way across here. So we're coming past Brazil and Rio de Janeiro, through Argentina, around, picking up cool energy, or lack of energy, in the Southern Ocean down here, and then around to the west coast of Africa, where we've got a cold current that comes around to the equatorial area. We split generally the Earth, when we flatten it out into a static map like this, with the Pacific Ocean. So I will do my best to give you this. Rotation is going to come across over here off the screen here. We're going to rotate up, so that's going to be over here. We're going to rotate up across past China, past Japan and Korea, through Kamchatka, Russia, where it's cold energy. We're going to come around the Aleutian Islands with cool energy. The California current on the west coast is cool. So west coast has a cool current and cool air. East coast, warm current, warm air. Likewise in the southern hemisphere, that rotation again is counterclockwise in the southern hemisphere. So we're going to rotate past in this direction. We're going to hit Fiji and Australia and New Zealand with a nice warm current in this location. Rotate around, come through the Southern Ocean, and then hit Chile and Ecuador through here with a cold current on the west coast again. We see similar rotations in the Indian Ocean. All right. So this is the last slide for this little set. And what I want to tell you here is that when the solar energy first interacts with those first molecules of our atmosphere, it engages in a number of different energy pathways. And basically, it's what direction and how fast and what wavelengths is that solar energy going to move. And those pathways are engaged through radiation. All bodies radiate energy. We mentioned the other day we've got active radiation like the sun, or passive radiation like a nice black car on a summer's day. You know that car, if you're going to touch it, it's going to feel hot. Solar energies come, it's hit that paint job on that car, and because there isn't any holding capacity of that paint on that car, it's going to re-radiate that energy back and give that energy off, and you're going to feel that as sensible heat. All bodies do this after they've received some amount of solar energy. They may radiate that energy immediately if they've got poor holding capacity, or they may store that energy for a little bit and then re-radiate it a little bit later. But all bodies radiate energy. The volume of energy absorbed by a molecule is going to be re-radiated at another period in time, a little bit later. So we said the other day that water has great absorption capacity. It's going to store a lot of water, and then it's going to give that it's going to store a lot of energy. It's going to give that energy back up at a later time. Some particles have exceptionally poor absorption capacity, and therefore they have no ability to give off heat at a later time. Reflection then, we're going to use a fancy word called albedo for reflection, and reflection is how much energy upon hitting an object is bounced back, is repulsed back into the atmosphere. Generally speaking, that energy is coming in at the same direction that going back out as the same direction it came in. So think of the reflection that you have with a mirror. A good quality mirror makes you look pretty normal, right? If the mirror is poorly made, the silver at the back of that mirror is a little bit wavy, or another compound's used, or the application of the silver backing on that mirror is not put on correctly, then you get a funhouse mirror, and you might look a little funky. Your head's a little big, or it's got a kink in it, or something like that. So that means that the light is bent. It is scattered. That's this next bit here. It is refracted. So the energy then is moving off in a different direction based on the particle, its density, and other characteristics. That's really important because scattering is going to provide energy to different locations on the Earth. So solar energy can come in at one location, and a molecule of a particular compound in the atmosphere may be quite dense, and then push that energy off into a different direction. So think of it this way. You may have a cue ball that you would play pool with, and if you push that cue ball into another billiard ball, and you hit it square on, that billiard ball should transfer that energy and move in the same direction that your cue ball was moving in. That would be similar to reflection. Sort of that there's not much scattering going on. If, however, you took your cue ball and you hit a kid's rubber ball instead, that rubber ball is going to absorb some of that energy. The cue ball is going to retract back in a different direction from whence it's come. So that energy is scattered then into a new direction. And the same thing happens on the atmosphere with the Earth, is that You might have some solar energy coming in at Mexico City, and depending on the pollution or the cloud cover in Mexico City on a particular day, that energy might be scattered into other parts of Mexico or into the Gulf of Mexico or the Pacific Ocean, and then those areas benefit from the scattered energy. Transmission then is how that energy passes through the medium of the atmosphere or the medium of the water. We talked a little bit about transmission the other day. So if you've got a pretty dense environment, then less light is going to transmit through. There's going to be a lot of particles that are going to interact with that photon of light that's going to come through. It's going to create far more scattering, and far less energy is going to be transmitted to the surface of the earth, and it's going to be a little bit cooler. Whereas if you've got a less dense environment, atmospheric environment, then the transmission is going to be much more straightforward. There's going to be less bending of light, less changing of direction through scattering, and more intense energy received at that particular location. All right, I am going to wrap up this set of slides, and we'll get on to the next set immediately.